Okay, resuming the video for MAC1105, section 4.5. I think we left off with problem number 6. So we're on to number 7. So an artifact originally had 16 grams of carbon. The decay model, so it's decreasing the number of carbon, and which is exemplified by this negative rate here. That means it's declining or decaying. Describes the amount of carbon present after T years. Use the model to determine how many grams of carbon-14 will be present after 9,908 years. 98 years. 9,998 years. So I'm going to take the formula right here. $16 grams initially. This is 0.12312. 123,121 with a T, and we're going to figure out how long it's going to, or how much carbon there's going to be after 900 or 9,998 years. Okay, so plug that in there. And then get your calculator and put all of that in. So this is called a decay model because the rate of decay is negative. Okay, so putting that in the calculator, you have E raised up to a power of negative 0.000121 times 9,998 times 16. And this turns out to be what's left. Let's see, use model term number of grams, round to the nearest whole number, so it's 4.77, so that's approximately 5 grams after this many years, declining at that rate. In number 8, prehistoric cave paintings were discovered. The paint contained 30% of the original. Use the exponential decay model for carbon-14 to estimate the age of the painting. Says the more carbon something has in it, the more alive it is. So the less carbon it has, that can tell you how long ago something expired. So as we go and use this model now, we have to hook into this phrase right here. The paint contained 30% of the original when they found it, years later. So we're going to put here, this is the original amount, which they don't even tell us. But they do say that in the end, when they go and look at it so many years later, there's only 30% of the original amount. So this is how you write 30%. Of means multiply, and A sub O represents the original amount. So here's the original amount on one side. We're using this model again from number 6. Final amount, original amount. And then it's E to the negative 0.000121 with a T right there. And we're supposed to be solving for T. And the reason we can do this, I know it looks like we have a lot of unknowns, is because we always divide this coefficient right off of the exponential term. So we'll do the same thing on this side as well. And because we have the same expression on both sides, it's not really like we have anything extra here. So this is just going to be any extra variables. So 1, 2, 3, 1, 2, 1. And then the A sub zeros are gone. And all you have left is 0.30. And then in order to finish something like this, what you're solving for is in the exponential position, and that's what the logs are for, as the last two sections have talked about. We could take a log of both sides, but a natural log would work better because on this side, on the right side, natural log of anything with a base e, these will cancel with each other. The augment and the base, take the word log with it, and so that is what brings this down out of the power position. So now we have negative 0.000121, but now it's not up in the exponential position. And then on the left side is just whatever the ln of 0.30 is. Let's put that in the calculator. So ln of 0.30 and I got negative 1.20397, and then all I have to do is divide by this coefficient. Likewise on the other side. That cancels. Let me just make sure that I press that in right. So it's 1.2 on the top of 397 divided by 0.000121. You don't have to put the negatives in because they cancel. And I got 9,950. And let's see, again it says round to the nearest integer for this one. So this was 9950.1, so that would be the nearest integer, and that is in years. At that 9,950 years later, there's only 30% of the original carbon left. Okay, finally, number 9, last problem of the last section. You made it. Okay, so now this one says, the growth model describes the population A of a country in millions. What is the country's growth rate? The growth rate is always the power, the coefficient of t. So this is the growth rate, 0.005. If you give that as a percentage, to turn any decimal into a percentage, you move this 2 places to the right. So this would be 0.5%. I'm not going to try and squeeze it into that box. How long will it take the country to double its population? And up here in the directions, they give you a formula for doubling the population. Okay, this gives the time for a population with a growth rate to double. So we're going to use that here. Okay, because we're trying to answer how long. So it's going to be ln of 2 over the k value, but as a decimal, 0.005. ln of 2, 0.005. Put that in the calculator. So let's see. So it's ln of 2 divided by 0.005, and you get round to the nearest whole number, so this is approximately 139 when you round it to the nearest integer. How long will it take for it to double? Approximately 139 years. Okay, that concludes section 4.5.